In this video, I'd like to summarize what we talked about in the previous one. So we talked about different states of matter and the different phase changes we had. And I just want to point out how they're usually drawn. So for example, we have water vapor over here, which is a gas. And then usually gases are drawn where the particles are quite far apart, because that's true. There's a lot of empty space in between particles when we're talking about a gas. Here we've got water, a liquid, and the particles are loose but drawn close together. And that's true because the particles really are close together. They're feeling forces between the different molecules. And then for solids, we usually draw them very close together and often with a rigid pattern, a regular pattern or a structure. And then make sure that you are familiar with the terms, so melting and freezing to go between a solid and a liquid, vaporization and condensation to go between a liquid and a gas, and then sublimation and deposition to go between a solid and a gas. And then just to be clear, vaporizing, sometimes it'll be said evaporation or boiling, and it's essentially all the same thing. And then just to refresh on classifications of matter, so in general, we can have mixtures or pure substances. Mixtures, it's more than one substance. Pure substances, it's just one substance, so every single particle in your sample is identical. And I have a bunch of practice problems within this PowerPoint so we can really practice the difference between something that's a mixture versus a pure substance. And then with regards to just mixtures, we have heterogeneous and homogeneous. And the difference here is, can you distinguish between those two or between the two or three or more components of the mixture just by visualizing it, by looking at it. So if it looks totally uniform, like maybe a glass of milk, then we would call that a homogeneous mixture. Or salt dissolved in water. You can't see the salt. You can only see that, it looks like water, but there's salt in it, but you can't actually see the salt. We would call that a homogeneous mixture. Whereas something like sand in water, and the sand has now settled to the bottom, we would call that a heterogeneous mixture because you can very clearly see that there's sand at the bottom and you have water in the rest of it. Another example might be like a oil vinegar salad dressing. You have to shake that before you put on your salad because everyone knows that water and oil don't mix. Oil likes to float at the top. The point is you can see the difference. You can see that there's oil in there and they separate out. That's another heterogeneous mixture. So heterogeneous mixtures are not uniform. Homogeneous mixtures are uniform. And then with regards to pure substances, we can have compounds or just elements. So a compound is when you have two or three or more different elements chemically combined. So you could have hydrogen and carbon and oxygen all together, and we would call that a compound. And an element is when you have just one element, so just hydrogen atoms or just oxygen atoms or just carbon atoms. And it could be a single atom, or it could be two of the same identity bonded together. So this might be an example of a helium atom, and this one might be an example of a hydrogen molecule. So then just to summarize again, make sure you're familiar with all of these terms. So if I said something was homogeneous, I'm saying it's a homogeneous mixture, which falls under matter. And then elements can be either atoms or molecules, and it could even be like three together. So the ozone molecule might look like something like this because it's three oxygen atoms all chemically combined to each other. They're all attached, but it's still all oxygen, so it's still an element. So I have a handful of examples. So in this first one, for example, if we wanted to classify this as an element or a compound, we have two different circles in the picture. So we've got like a large open circle and then a small dark circle. So we can't say it's an element. So I would classify this as a compound. And then if this is a pure substance or a mixture, all four of the particles in this little box are the same. So I would say this is a pure substance, so a pure compound. In this next one, we've got clearly two different things, and they didn't draw the circles touching, so they drew the circles far away from each other. So that implies that they're not chemically combined. So here we certainly have a mixture, and then because each circle, these are kind of like atoms. You know, this can be a mixture of elements, if anything. Could be, you know, helium atoms and neon atoms, for example. A mixture of two different elements, and they're not combined, so we're going to call them a mixture. In number 3, so it looks like all of the particles that are drawn are identical the way they look. So this would be a pure sample of something. And then since we've got two different circles, white circles and black circles, this would be a compound. Next one, same kind of thing. All of the particles given to us are the same. So this is pure. And the two different colors are implying it's two different elements. So we can't say it's an element, it's a pure compound. Number 5, we've clearly got two different types of particles. We've got this particle where we've got 3 circles, and then we've got this type of particle. So this is a mixture. And then we could say it's a mixture of compounds. For this one, we've got two different types of particles. We've got these particles where it's 2 white circles, and this particle where it's a black and a white. So this is a mixture. But this one here, I would call that a compound, and then this one I would call an element. So there's a mixture of an element and a compound. Okay, a few more examples. So number 7, all of the particles drawn look the same. So I'd say this is pure. And then it looks like within a single particle, all of the little circles are the same. So this would be a pure element, where the element in and of itself is a molecule. And the perfect example for this one, looks like the ozone molecule, which we would say O3, which we're going to get into in the same presentation, this way of writing formulas for molecules. Number 8, so we have a mixture. And this looks like it's a mixture of elements. Because here, both little circles are the same shading, same color, and here they're the same. So we can call this an element, and we can call this an element. But then within the box we have a mixture, so it's a mixture of elements. In the next box, notice here we've got 3 circles, here we've got 2, so I'll call this a mixture again. And then here, since the 2 circles are, we've got white and black, and here white, black, and white, these are not elements, these are compounds, so I'll say it's a mixture of compounds. Next one, so all of the little circles that are in, or all of the little particles look like they've been drawn the same, white, black, white. So this is pure. This is a pure compound. Same kind of thing here. Looks like we've got compounds drawn as opposed to elements. And all the little particles have been drawn the same. So I would call this a pure compound. Number 12. This one also looks like it's pure, but now each little particle is made of 2 circles that are the same color, so we'll call this a pure element. And an example of what this really could be representing, this could be like H2 gas, hydrogen gas, it could be O2 gas, oxygen gas, because those are part of our diatomics. So I don't think I mentioned it last time, but there's a handful of elements that naturally occur as 2 atoms chemically bonded together, and that's just how they naturally are, and there's 7 of them total. And this slide is duplicated, I'll skip that one. So then here's one where it says consider these 4 containers labeled A, B, C, and D. Which of these are mixtures? And then which ones are pure substances? So this one, A, looks like it's pure. This one, B, is definitely a mixture. C looks like it's pure. And D is definitely a mixture because we've got 2 different particles here. And then this particle, hopefully you might recognize what that's trying to look like from the slides, but this looks like it's trying to be the water molecule, H2O. Okay, which one contains only compounds? So in box A, I'd say this is only a compound because these circles kind of got gray and white, so I'll put A. And then we can't say B contains only compounds because that looks like it's an element. This is an atom of something, and this is a diatomic. This is two of the same, so I'll put, well, I can't put B under when it doesn't contain only compounds or only elements. It's got a mixture. C looks like it's only elements because all of these little drawings are the same. D, however, I could probably put under only compounds. It's a mixture of compounds, but it does contain only compounds. That's true. Next one, which of these are mixtures? Which of these are pure substances? So this, B, looks like it's certainly a mixture. And A also looks like it's a mixture. We've got kind of gray circles and dark gray circles. C as well. I agree we could put C under a mixture. Now in D, it looks like all of those little circles, they're trying to draw it the exact same way, so I'd put D under a pure substance. Which contains only compounds and which contains only elements? So I would certainly put C under only compounds because all of the particles being drawn, the individual circles within each particle is different color, so that implies it's a compound. D, because all of the circles are the same shading, that looks like it's an element. Now compounds, remember it's two different elements chemically bonded together. Now I'm thinking about choice B. So B, I would probably put under only elements because it looks like none of these circles are actually supposed to be touching each other. They're just very, very close. So B, for example, looks like a mixture of elements to me. So that's why I'm thinking I'm going to put B over under only elements. And then A looks like it's a good example of, for example, like sodium chloride, a crystal lattice structure or something. But I'm going to put that under only compounds, and we can talk about that in another slide once. I think in the week 3 lesson, once we start talking about different types of compounds and stuff. Okay, so then this one. So which ones are mixtures? Which ones are pure? So A looks like it's pure. And then D looks like it's pure. In fact, all of these look like they're pure. Because a pure substance just means, again, all of the particles being drawn. So actually all of them. So none of them are mixtures. Which contains only compounds, and which one contains only elements. So A looks like it's an element. B looks like it's a compound. C is a compound. And D is an element. Which one of the containers are gas, liquid, and solid? So again, in the very first slide, we talked about how they're typically represented solids. They're very, very closely packed together in a rigid pattern. That looks like what we see with D. Gases, there's lots of empty space between the particles. So that looks like C and A. And then liquid, they're close together, but they don't have a regular pattern. So that looks like B. Okay, so hopefully that was helpful. Recall from last time we talked about the different types of elements. So very broadly, we classify the periodic table. We split it where we have metals on the far left side, and then the stair-step pattern that goes between the metals and the nonmetals. That's the metalloids. And we usually have agreement, within science which are metalloids, but sometimes you might find a source that says aluminum is a metalloid. But I think most would consider aluminum a metal. But it's generally that stair-step pattern. So on my periodic table that I have on my wall, the metalloids are listed as boron, silicon, germanium, arsenic, and yes, I think I got them all. Those are the ones that are listed on mine in that stair-step pattern, and it might be ever so slightly different on other periodic tables you find. And then the ones on the right, those are your nonmetals. And it's just important to recognize the metals between the nonmetals because later when we start talking about types of chemical bonding, you need to be able to identify, do I have a metal attached to a nonmetal? Because if I do, that determines what type of bonding is in that compound, and that determines how I name the compound. Whereas if I have a compound that's only nonmetals, we have a different rule for naming compounds that are made up of only nonmetals. So then next thing, just summary of properties. So make sure you're familiar between the differences. So, one important difference, metals are usually shiny, non-metals are not. There's no metals that are gas. Non-metals, there's a handful of them that are gas. And with each of them, with metals and non-metals, there's one that's liquid at room temperature. For metals, it's mercury, that's a liquid at room temperature. And for non-metals, it's bromine, that's a liquid at room temperature. Those are just important exceptions, and most periodic tables will have those labeled for you. The one that we have in the classroom, they use a different color font, but these will commonly be labeled somehow. The densities, so metals usually have a high density, non-metals usually have a low density. Another very important physical property is conductivity, so metals conduct heat and electricity very well, and non-metals are usually non-conductors. So the next thing that's new, so we have law of definite composition, or sometimes it's said law of definite proportion, but it states that compounds always contain the same elements in a constant proportion by mass. So water is always this much hydrogen and oxygen. So another way to put that is water is H2O, and water will always be 2 hydrogens and 1 oxygen. Every single molecule of water is always going to be 2 H's and an oxygen, no matter where you get that water from. And then another example is methane. Methane is CH4. Methane is always going to be 1 atom of carbon and 4 atoms of hydrogen. And then they're emphasizing, by mass, because if you were to actually weigh out a sample of water or methane, because carbon atoms have mass and hydrogen atoms have mass, it's always going to be the same percent by mass. And we can figure that out, and we'll do practice problems with that where I demonstrate how to actually get these numbers. But that's what we mean by law of definite composition. These molecules, water, methane, other molecules, they will always be in the same ratios. So I've kind of been mentioning these, so like the term molecule I've used quite a bit so far, and I just showed you some chemical formulas. But a unit of matter composed of 2 or more atoms is a molecule. And we say non-metal because when we have a metal and a non-metal, we don't really want to call it a molecule. We'd rather call it like a unit. So for example, NaCl, that's table salt, sodium chloride, it's technically not really a molecule. So we might throw the word molecule around, but molecule is really like non-metals, and it has to do with the way they're bonded. So this one is, not really a molecule. But we'll worry about that a little bit later. And now a chemical formula is an expression of the number of atoms of each element in a compound. So here's their example. We have this H2SO4. This guy is called sulfuric acid. Maybe you've heard of it before. It's common in car batteries. But by the formula of sulfuric acid given here, it's telling us that we have 2 atoms of hydrogen because of the little 2 right there, 1 atom of sulfur, and then 4 of oxygen. And it's important to notice that we're using subscripts here, so we're not saying H2SO4, we write H2SO4. So we're using subscripts. And if you were going to try and type out formulas, for example, in your homework using Microsoft Word, you can tell Microsoft Word to use these little subscripts, and that's the proper format for writing chemical formulas. But these little numbers carry over. This 4 is telling us we have 4 oxygens, and this 2 is telling us we have 2 hydrogens. Notice there's no subscript for the sulfur, because we usually leave off subscripts if it's just intended there's 1. So another example, H2S, hydrogen sulfide. This is 2 hydrogens and just 1 sulfur. There's no subscript 1. We don't do that. So next thing, writing chemical formulas. So I kind of just did this with the first example, but here's another one. The name of each type of atom in a molecule is indicated with a subscript. And if there's only 1, we don't type out the 1. So here's an example. They've got vitamin B6 right here. So this would have 6 carbons and 6 hydrogens and 2 nitrogens and then just the one oxygen. And this is also usually the order. So when we have organic molecules, we like to write carbons first, and then hydrogen second, and then the other atoms after that. But there isn't necessarily a strict rule to that, but usually with organic molecules, we'll put the carbons first. That's just kind of a common thing. So then interpreting chemical formulas. So sometimes you'll see parentheses used. So for example here, this is the formula for ethylene glycol, a component of antifreezes. So notice the parentheses, we're trying to say that it has 2 carbons and 4 hydrogens, but then we've got these OH units. So if we actually looked at the structure, it would make a little more sense perhaps, because you'd have these oxygen-hydrogen units on the molecule, but we're using parentheses, and then there's a 2 outside of that. So that 2, it's kind of like it's being carried over to both of them. Kind of like how you might carry over multiplication in math. If you had 2, times 4 plus 8, you could carry that 2 to both of those and do the problem a different way. It's the same kind of thing. So that 2 is being carried over, and that can help us count. So how many total atoms? So we've got 2 for carbon, 4 for hydrogen, and then this 2 is saying we've got 2 oxygens and 2 more hydrogens. So 2 plus 4 plus 2 plus 2, we get to a total of 10. Now we could, it's not wrong to combine these hydrogens. So you might see the formula, if you were to like Google ethylene glycol, you might see it written like this. That's not wrong. This is just a different way of writing the formula. The point is, if you do see parentheses, that's what it means. That 2 is being carried, and it's being applied to that on the inside. Now, sometimes we do want to make sure we stick with the parentheses when we talk about polyatomic ions, which is not for this lecture, but we'll do that later when we see those parentheses come up again. Okay, so next thing, and this is the last little bit for this video at least. So Lavoisier found that the mass of reactants before and after a chemical reaction was always the same. So the mass of the reactants before a chemical change was always equal to the mass of the products afterwards, and we call this the law of conservation of mass. So basically it's also saying matter is neither created nor destroyed in a chemical reaction. So then just some examples of what we mean. If 1 gram of hydrogen, so I would be saying like H2 gas, combines with 8 grams of oxygen, O2 gas, we've got 1 and 8 as our reactants, 1 gram of hydrogen and 8 grams of oxygen, those are our reactants. And then we have 9 grams total of water that was produced. So we had 9 grams beforehand, we have 9 grams after. Another example, 3 grams of hydrogen combined with 24 grams of oxygen to produce 27 grams of water. So again, we had 3 and 24, that was the mass of our reactants, the amount of stuff that we had before the chemical reaction happened. And that adds up to 27. 24 plus 3 is 27, and we have 27 grams of water afterwards. No mass is lost. Another example, we've got 50 grams of water, and it decomposes to produce, so our only reactant is the water. It decomposes to produce 45 grams of oxygen. How many grams of hydrogen are produced? So we had 50. This is our reactants, 50 to start off with. So that means the sum of the products must also be 50, so that's why they're doing a subtraction. The mass of the products must be 50. We know that some of the products was oxygen at 45 grams, so the rest of the mass must be 5 grams for hydrogen.